And good evening, AP Physics students. Mr. Curse coming at you here, talking about a little heat today. Perfect time of year now that it's spring out and we're starting to feel that heat outside. We're going to heat up our discussion here of thermodynamics. So let's talk about heat here for a minute. What is heat? Well, physicists like kind of broad, basic definitions. So to a physicist, heat is energy transferred from one object to another object because of a difference in temperature. Okay? And we remember that temperature is a measure of the average kinetic energy of the particles of a system. So if two objects, if energy transfers from one object to another because there's a difference in temperature, we call that energy transfer heat. Okay? So temperature is a measure of the average kinetic energy of an object. Heat is the amount of energy transferring from one object to another object. The SI unit of heat is the calorie, and that's abbreviated with a little CAL. 1 calorie is the heat needed to raise 1 gram of water 1 degree Celsius. Notice that these are lowercase c's. Sometimes in literature, a capital C means a dietary calorie, which is really 1,000 lowercase c calories. We're going to stick, we won't use that in physics. We'll just stick to calories. And for that matter, we'll probably stick more to joules. All right. So a calorie is defined by heat, where remember that a joule is equivalent to a Newton meter. All right. So it was Joule who originally found what we call the mechanical equivalent of heat. And I'm going to show you a picture here of how he did it. So what Joule did was the following. He designed a little experiment that looked like this. He dropped a weight, okay, and figured out what the mechanical energy of this weight dropping here. And this weight turned these paddle wheels, and because of the internal friction and fluid dynamics there, the water heated up. So he got a conversion between mechanical energy, joules here, and calories here. So we call this the mechanical equivalent of heat, and it's how we get the accepted value today that 1 calorie is actually 4.186 joules. Okay? So this is defined by mechanical moving of things. This is defined by temperature. So a little bit of a difference there in definitions. Okay, there are 3 ways in which heat can transfer from one object to another. And they are conduction, convection, and radiation. All right. Conduction is when a hot object is in physical contact with a colder object and heat flows between them. Convection is caused when you have fluids, either air or water, and basically hot air rises and cold air sinks, and you get convection currents formed, whether they're in water or in a house. But hot air rises, cold things sink, and you get this movement of fluids. All right, we call that convection. And of course, you guys know plenty about radiation. In conduction and convection, 2 things have to be in contact, whether they're solids in conduction or liquids in convection. Radiation, for instance, radiation that comes from the sun, there is no material object between the Earth and the sun. So radiation like light or infrared radiation or UV radiation or X-rays or gamma rays, any part of the electromagnetic spectrum doesn't need a medium to transfer through. So it's the only one that can transfer without touching. So 3 ways heat can be transferred from one object to another. And the one we're going to spend the most time talking about is conduction. Okay, there are 3 things that are important when measuring the rate at which heat will transfer from a hot object to a cold object, right? And Q here is heat, usually measured in joules or calories. T is time, usually in seconds. So the rate of heat transfer is dependent upon three things. I'm going to show a little picture here. It's dependent upon the temperature difference between the hot object and the cold object. That's where we get delta T. So obviously the larger delta T, the larger the heat transfer. It's dependent upon the length of the object between them. The longer the object, the less quickly the heat would flow there. So the rate is inversely proportional to the length. It's directly proportional to the area of contact. More hot molecules touching more cold molecules, the faster. The fast-moving, hotter molecules will give some of their energy as heat to the colder, slower-moving molecules. And it depends upon the thermal conductivity of the substance in question. You can see here thermal conductivity is, we give the constant K. And you can see that metals have very high thermal conductivities. This is why in the winter, even if someone double dog dares you to stick your tongue on a stop sign, you shouldn't, because metals have high thermal conductivities and the heat will quickly flow out of the saliva on your tongue and freeze your tongue right there. Air, polyurethane, goose down, wool have very low thermal conductivities. They're good insulators. They're good things to make things out of when you don't want heat to transfer, like a jacket or insulation. So as we said here, the constant K is defined to be the thermal conductivity. And if you need to find that, check out table 14-4 on page 396 in your book. That'll give you values for different substances. And I think that's all I have to say here, and we better get on with problem 33 here. Okay? So problem 33 states I have a hot object that is 460 degrees Celsius, and I have some cold water at 22 degrees Celsius. I have a rod of aluminum that is between these two objects. The rod is 33 centimeters long, and it has a diameter here of 2 centimeters. All right. And let's see, there's one other piece of information. Oh, and that's all we need to know. All right, so the question here gives us that information, then asks us to find the rate at which heat is being transferred between these objects here. So I'm going to pull this equation down here and say Q over T is equal to K. Now we would look up the K value here for aluminum, which looks like about 200 is the value for that, times the area here. Well, if this has a diameter of 2 centimeters, that would be a radius of 0.01 meters. All right, let's see, let's do 0.02 divided by 2 squared. That would be the area, okay? Our temperature difference would be 460 minus 22. Okay, so we got that in there, and the length here would be 0.33. Notice here I'm using all meters for my units, and for my temperature difference, I can use either Celsius or Kelvin, because remember the temperature difference between two objects will be the same, whether it's Celsius or Kelvin. And if I plug all that in, I will get a rate of heat transfer of 83 joules per second, or I could also label that watts. Okay. All right, nice work, AP Physics students. Speaking of radiation, be on the lookout here for some radiation this week. Scientists are predicting that the sun is now, and in the in its peak of its 11-year radiation cycle. So speaking of radiation, be on the lookout for sunspots this week. All right, nice work, AP Physics students. We'll see you tomorrow.